So we're talking about power and radical functions today. Before we can do that, you need to know a little bit of terminology, which is continuity and in behavior. These two words are going to come into play since this particular part of functions, we're talking about other types of functions, quadratics, power, radical, other polynomial functions. And so you're going to need to know these two terms because you'll be asked to describe the in behavior as well as determine if there are any types of discontinuity. So today you're going to learn about not only how to graph power and radical functions, but also how to describe in behavior and determine and classify discontinuities. So a continuous function is one that has no breaks, it has no holes, and it has no gaps in it. Okay? A continuous function is when you look at a graph and it has no breaks in the graph, it has no holes, it has no gaps. Okay? So if you look at this picture that you see up here on the screen, is this a continuous function? No, it is not. It has a what in it? It has a hole. That open space that's on the graph, that is a hole. So that function, or whatever it is not continuous. Another good rule of thumb is that you can start on the graph, and if you don't have to pick up your pencil to continue the graph, then it is continuous. Okay? So if I wanted to trace along this graph, I have to pick up my pencil to avoid the hole to keep going. That means it's not continuous. I should be able to trace along it without having to pick it up. Okay? Now, this whole concept of a continuous function is the very first idea behind limits, which is the foundation of calculus. It's pre-calculus. So you're getting your foundations that you need to continue forward. Okay? So we're going to be talking about limits in very minute form today, but we will revisit them again at the end of the year. There are three types of discontinuity. You have infinite discontinuity, which is the same thing as having an asymptote. Okay? A vertical asymptote, let me be more specific. A jump, which you see a lot of in piecewise functions. And removable, which is also called a hole. Those are your three types of discontinuities. And all these graphs that you see on this picture, none of them are continuous. Every single one of them has some type of discontinuity. Okay? Like in this first one right here, you have jumps, you have infinite discontinuity, okay, because you have an asymptote and you have to go from this point to continue, and then this point to this point, and so on and so forth. Okay? This one up here at the top, number 2, what type of discontinuity does it have?
Jump.
It has jump discontinuity. What about number 3? It's hole. Okay? You need to be able to identify what type of discontinuity it is. It's going to be one of those 3. Okay? So when you start graphing some of these power and some of these other types of functions that you're going to get, it is going to ask you, is this graph continuous? What type of discontinuity does it have? If it's not. Okay? Questions on that? All right. In behavior. In behavior of a function describes how the function behaves at either end of the graph. Okay? In other words, mathematically, it's asking what happens to the value of f of x. What does f of x mean? Y. So it's asking you what's happening to the value of y as x is increasing or as x is decreasing without bound. Okay? To describe in behavior, you use limit notation, which is what you see right here. This is limit notation. The LIM stands for limit, and it's saying the limit as x approaches negative infinity of f of x. Okay? What that basically means is it's saying without bound, without any restrictions, without stopping the graph, as x gets closer to negative infinity, what is happening to the y value? That's what that whole sentence that's in that box is saying. without any restriction, as x is getting closer to negative infinity on your graph, what is happening to y? That is known as left-end behavior. Because if you think about it, it's a negative infinity on your left-hand side. Okay. So you have the left side of the graph, and you will have a right side of the graph, right-end behavior. The limit as x approaches infinity. So without bound, as x gets closer to positive infinity, what's happening to y? And it will either approach positive infinity, negative infinity, or a specific value. Your job is to look at the graph and say, okay, as we approach the end of the graph, as the graph keeps going closer to infinity, either positive or negative, what's happening to y? Is it getting bigger? Is it getting super small? Is it leveling out at a specific number? Questions on that? Any questions? So just to make sure that you guys understand, I'm going to take this particular graph, okay? Yes, it's not continuous, but that does not mean that I can't describe the end behavior, okay? So, the limit as x approaches negative infinity of f of x, it equals what? What is the limit? So then we do have questions. As x gets closer to negative infinity, what's going to happen to this graph beyond that arrow? And what is the y value down there? That's your answer. So as x continues to get bigger and bigger, because I can continue this all the way out to negative 100, negative 1,000, and so on and so forth, this graph is going to continue to keep going down. And the y values down here go closer to what number? That's your limit. That's your end behavior. As x gets closer to negative infinity, y is getting closer to negative infinity. What's the right end behavior? And how do you know that? Because it keeps going up. As x gets bigger and bigger, that graph is going to continue to go up. Let's look at another one. What about here? Describe the end behavior for this. You got to be specific. As x approaches negative infinity, which one is it? Negative infinity. You have to write this entire sentence to describe the left end behavior. To describe the right end behavior, you have to write this entire sentence. What is it? Positive infinity.
So it's just going to be the direction that it's going.
You got to look and see exactly what's happening. Not so much the direction, but more so what's happening to the y value. Is it increasing without bounds? Is it decreasing? Is it leveling out? Like if you look at this one right here, I'll put an arrow here and I'll put an arrow here. And let's say this is negative 5. How would you describe the left end behavior here? As x approaches negative infinity, what's happening to the y's? It's negative 5. Because this means that it's going to stay what? Afterwards.
It's going to stay negative afterwards.
And what's that called when it's flat? It's called constant, staying constant, negative 5. What about when x approaches positive infinity? What's going to happen? Is it going to cross over the x-axis to go to negative infinity? It's going to what? Level out to what value? 0. It's what happens to the y's. The x-axis means that y is 0. So as this continues to level out, that y value is 0. So it can be positive infinity, negative infinity, or a specific value. You got to be able to look at the graph and be able to describe what those values are. Questions? Then let's apply them to these power and radical functions. So now we're talking about your power and radical functions. You're going to learn how to graph and analyze each of these power and radical functions. All right, you have your power functions. Those are the types of functions that are in the form of f of x equals ax to the n power, where x is a non-zero constant number. A non-zero constant number. So that could be 3, -1, 5, so on and so forth. Okay? And these, what you see on your paper, are the different types of graphs they're going to look like. Okay? So n is an even number and a is positive. It's going to look some variation of a quadratic that points up. Now, that's not saying that every one is going to be to the second power. This can be something equivalent to 3x to the fourth power, for example. Even 3x to the fourth power is going to look some variation of a quadratic. Okay? In other words, both its ends are going to point up. However, if n is even and a is negative, it's going to be a reflection over the x-axis, and it's going to point down. So that would be like -3 to the sixth power. If n is odd and a is positive, then it's going to look similar to a cubic function, where the left end behavior is negative infinity, the right end behavior is positive infinity. So that would be an example like what? Someone give me a positive a value and an odd n value. 4x to the third power. That would be an example. Or it's going to look like what you see on the bottom right, where n is odd and a is negative. Give me an example of that. Or fifth. Let's change that. Okay? So those are examples. So even if, let's say, you forget that golden rule of how to graph any function, what's that golden rule? If you forget how to graph anything, you make a table. Let's say that just flies your mind, but then you remember this stuff right here, then you at least have an idea of what it looks like, okay? And maybe even potentially be able to analyze the graph without actually seeing it. So that's what we're going to be doing today. We're going to be graphing up about 6 power functions, types of power functions, power and radical, and classifying them, okay? I'll do probably the first one all the way with you guys, and then after that, I'm going to kind of let you guys do them on your own. Okay? Because it's pretty much as simple as this. Okay? Being able to look at the graph and analyze. And we talked about domain and range before. We have. Domain is your what values? Range is your?
Y.
And the intercepts, there are 2 different types. There are X and Y intercepts. In behavior and continuity I just talked about. So when you're writing your in behavior, you know you're going to have a left in behavior and a right. And you need to make sure you use that proper notation. And then how many types of discontinuities are there?
3.
There's 3. What are they? Jump, pole, or removal, and infinite, which is an asymptote. Now, not every power function is going to have those. So if it doesn't have any of those types of continuity, you say none. Simple as that. But if it does, you say what it is and where it is. And we talked about increasing and decreasing back in Unit 1. Increasing means where the graph is. Going up, decreasing. Going down, okay? Now, even though we have an idea of what a 1/2 x to the fourth look like, because a is positive and n is even, let's still make a table. Doesn't hurt to do a few negatives, 0, and a few positives. So in that way, you have a good representation on the left and the right side of the y-axis, okay? I'm going to start with 0, because when I plug 0 in, 0 to the fourth times 1/2 is going to be 0. Because 0 times anything is going to give you 0. 0 raised to any power is going to give you 0. If I plug in -1, what's -1 to the fourth power? And I multiply that by 1/2 and I get 1/2. So at -1, I'm at 1/2. When I plug in -2, I apply the power because its order of operations was -2 to the fourth power. And what's 16 times 1/2? Now this one, unfortunately, is going to be off the graph, but it's going to be somewhere up here. When I plug in 1, what do I get? And when I plug in 2, what do I get? And that's how it looks, very similar to a quadratic. But it's not a quadratic, it's actually a quartic. Bless you. There you go. Analyze the domain. Somebody in this side. What's the domain of this function? Wait, this side. Negative infinity to infinity. You can give it to me any way, whichever way you feel more comfortable. Somebody in the middle section. What's the range?
From 0 to infinity. With brackets on 0.
Bracket on 0. Parentheses around infinity. This side. Do I have any intercepts? I got x-intercept. 0 what? 0, 0. And it's actually an x and a y-intercept. Is that the only one though? Do I have any more? Now the end behavior. Okay? I'm going to do it down here because my handwriting's not going to fit in that little space. Okay? The limit as x approaches negative infinity of f of x. That's going off towards the left-hand side. This graph will continue to get bigger and bigger and bigger. So what's the limit as x approaches negative infinity?
Infinity.
Positive infinity. Very good. Okay? The y's are just going to keep getting, bigger. And then the right end behavior, the limit as x approaches positive infinity.
Infinity. Positive.
It's going to be positive infinity. Again, you look. This graph's going to continue to get bigger and bigger and bigger. That's going to positive infinity. Yes, it can be the exact same thing. Because think about, just ask yourself, what's happening at the ends? It's getting bigger. Just keep going up. Okay? So that's what's happening with the y's. They're going to keep getting bigger and bigger and bigger. Continuity. Is it continuous?
Yes.
That's right. There are no holes. There's no gaps. There's no breaks. So continuous, continuity, it is continuous on the entire interval from negative infinity to infinity. Is it increasing at all?
Yes.
From where to where?
From 0 to
Is it decreasing anywhere?
negative infinity.
And you have just graphed and analyzed that function. And that's what you're going to be doing a lot of graphing and analyzing using what we did in Unit 1. This unit, nothing in Unit 2. Yeah.
Decreasing for the zeros. Can you just do parentheses around them, or do you have to be specific with brackets?
No, you would use parentheses because at that point it's a turning point, so it's neither increasing nor decreasing at 0. Good? Okay. When you use your table, when you make your table for this one, be careful. Apply the power, then make it negative. Okay? Because there's technically a -1 on the outside there. So you raise to the 5th power, and you multiply by -1. Okay? Go ahead and graph this and analyze. I'm going to give you 3 minutes. Now, this is an example where n is even, n is odd, and a is negative. Okay? So hopefully your graph looks like this one right here. Did it? It should have. Okay? Now you're making me question. Let's make the table first, okay? -2, -1, 0, 1, and 2. If I plug in -2, I'm going to do what to it first? Anyone? Raise to the 5th power. -2 times -2 is a +4. times negative 2 is a negative 8, times negative 2, which is a positive 16, times 2 is a negative 32. But then there's a negative on the outside, which means it becomes a positive 32. You got to be careful, especially when negatives are involved in signs and odd powers. When I plug in negative 1, what's the y, corresponding y? It's a positive 1. When I plug in 0? When I plug in 1? Negative 1. You do 1 to the 5th power, then you make it negative. And then when you plug in positive 2? And that's how you end up getting this cubic looking function where that one's like all the way up here and that one's all the way out my screen. Okay? So to describe this, Paige, what's the domain?
I got negative 52.
Very good. Kennedy, what's the range?
Negative infinity to positive infinity.
Very good. Aurora, what are my intercepts? 0, 0, yes. Another origin intercept. Describe my in behavior, Mia. Give me my left in behavior.
Is it the limit x to negative infinity f of x equals positive?
Very good. And I need my right in behavior. Valeria.
The limit of x to infinity
Mm-hmm.
is infinity. Positive infinity.
Careful. The right is this side. So it's actually going to be negative infinity. It's going down on the right hand side. Jose, is it continuous? Yes or no? Yes. Because there are no holes, no breaks, no jumps, no gaps, no nothing. I can continue all the way through. It is continuous on the entire interval. There is no bounds. There is no restrictions. Samantha, is this graph increasing? If so, where? Well, first, is it increasing? Question mark. Be careful. Make sure you read it from left to right. So if I read from left to right, this graph is actually going to be decreasing the entire time. So it's not increasing, but it is decreasing from anyone.
Negative infinity to
So you gotta be careful. Make sure you read left to right. Sometimes we're so tempted to start from like that middle point and then go back and then go forward. Always go from left to right. Okay? Question.
So anytime it's continuous, you always just put negative infinity.
Because remember we're restricted without any bounds. But if there's a hole, if there's a break, you make sure that you identify what it is and where it's occurring. Okay? Any questions on these type? Try to give you one of each, one even, one odd. Yes?
Can you just repeat how you read the end behavior sentence?
So the limit as x approaches whichever infinity of f of x is the answer. Other questions? Now, when n is less than 0, the power functions will look like what you see there, x to the negative 1, f of x equals x to the negative 2, and so on and so forth, okay? And they are undefined at x equals 0. These functions will have discontinuities. These functions will have discontinuities. Because back in Algebra 2 and back in Algebra 1, you learned that if you have a negative exponent, well, you never really worked with negative exponents. You made them positive by doing what? Making it like a fraction and putting it in the denominator with the positive exponent, correct?
Yeah.
And when we talked about domain and ranges, whenever we had a fraction, the denominator could not what? Equals 0. Hence, y is undefined at x equals 0, because if I plug 0 in here, it's going to be undefined. And it doesn't matter what number is up there, as long as it's negative. When I said x squared equals 0, it's still going to x is still going to equal. If I say x squared equal to 0,
A equals 0.
X is always going to equal 0. So X will not equal 0, and so on and so forth for the rest of the goods. Okay? So, be aware of those. Anytime you have a negative in your exponent. So, let's graph this. Do this one together. And my suggestion to you is that when you do see one with a negative exponent, rewrite it so that the exponent is positive, especially if you're going to be plugging in numbers. Okay? That negative 6 only applies to the x, not the 2x, just the x. If you brought the 2x down, that means that it should have been in parentheses raised to the negative 6. But now that I have that, I can make my table. If I plug in negative 2, what's negative 2 to the 6th power? It is 64. 2 over 64 is a really, really, really tiny number. 1 over 32. That's really, really, really close to 0, is it not? I'll plug in negative 1. Negative 1 to the 6th power is, so 2 over 1 is 2. If I were to plug in 0, what happens? And you can't have that. So that means it's undefined at 0. What occurs at 0 is what we call an infinite discontinuity. It is a vertical asymptote. Vertical asymptotes are drawn with dotted lines. So our horizontal asymptotes, we'll get to that when we talk about fractional. What do I get when I plug in 1? 2. And if I plug in 2, I'm going to get that doesn't give you much to work with, does it? It doesn't. Okay? So that's my, just for graphing purposes, so that way you guys can see it a little bit better, I'm going to do a few more points, just so you guys can see it. If I plug in a positive 3, 3 to the 6th power is going to be, what type of number? What type of number is 3 to the 6th power? If you don't know it off the top of your head, it's fine, but what type of number you think it's going to be? Huh? Like, it's going to be positive, and it's also going to be what? A big number, right? Because think about it. We have 3 to the 4th power is already 81. 3 to the 5th power is 243. 3 to the 5th power is going to be bigger than that. You have 2 over a really big number. 2 over a really big number is a really small number, is it not? 2 over a big number is a really small number. So at 3, it's going to be a really small number. Is it going to be negative though? It's going to be very close to 0. Same thing's going to happen when I plug in 4. Same thing's going to happen when I plug in 5. It's going to be so small that that number is going to get very, very, very close to what number? To 0. It's never going to pass 0. But what if I plug in 1/2? Like that's 1/2 is in between 0 and 1. 1/2 to the 6th power is what? Well, what's 2 to the 6th power? 64. So this is going to be 2 over 1 over 64. What do you do when you have a fraction within a fraction? So this is really 2 times 64 over 1. What's 2 times 64? A bigger number, 128. So when I'm at 1/2, I'm all the way at 128 up here. So this graph is going to get that the y values are going to get really, really big as x gets closer and closer and closer to 0. Is everybody following along? Like, you can plug in as many numbers as you need to so that you can see it, but the smaller the number gets, the bigger the y value is going to get. You're going to end up doubling it, like doubling the percent. What do you think is going to happen on this side? Exactly. It's going to be really small going this way, really big going this way. Questions? Yes?
So on this sheet, is this like the ones that have an even n and a positive a should look like, or an even n and a negative a should look like that?
But see, that's if n is a positive number. These are all negative numbers. So our exponents are all negative. Yeah. And this is the thing, when our exponent is negative, it's not going to follow the rules of what you saw on the front side. They're going to look like this. Okay? When a is positive and it's going to be a negative even, they're going to look like this. The one that you guys are going to do on your own for the next one is what they're going to look like. It's an odd negative. Okay? Let's look at the domain. I have an infinite discontinuity, which provides a break in my domain. What is going to be my domain? Negative infinity to what?
Negative infinity to 0, but the 0 has a parenthesis.
But the 0 has a parenthesis because this graph, this is not defined as 0. So it can't be a part of my domain. And I connect them with a union. What's the lowest this graph goes?
0.
What's the highest it goes? Am I defined at 0? Huh? Right. So that's what, yeah. So then we got any parentheses, right?
Yeah.
There we go. Do I have any intercepts of any kind?
No.
No, because it doesn't cross the y-axis because it's undefined there, and it never crosses 0 either. So I don't have any intercepts. Let's describe my end behavior. The limit as x approaches negative infinity is what? It's 0. As x gets really big, as it's going to continue, this graph is never going to cross that x-axis. This is one example of where it approaches a specific number. What about the right end behavior?
0. Well, it doesn't all the way up.
But I'm going this way. So that one is 0 as well. Is it continuous?
No.
There's an infinite discontinuity, and where does it occur? More specifically, x equals. Is the graph increasing at all?
Yes.
From where to where? Because again, we read from left to right, and this graph is increasing until the asymptote. And what's happening after the asymptote? This is the same thing as saying 2 over x to the 3rd power. Did you do that? Would have been helpful. Because now when I make my table, we can never switch colors. When I plug in -2, -1, 0, 1, and 2, it makes it a little bit easier to raise to a positive power than a negative one. What's -2 to the third power? To the way. It's a positive or negative. It's a -8. -2 to the third power is a -8. 2 divided by -8 is a -1/4. When I plug in -1 and raise it to the third power, that gives me it gives me a -1, and then when I divide it by 2, it gives me a -2. If I plug in 0, what happens? It's undefined. And what type of discontinuity is that? What's that called? It's called infinite. There's a vertical asymptote at 0. At x equals 0, there is a vertical asymptote, which means the domain is not going to be -infinity to infinity. It has that break there. Okay? Oops, and I put this down in the wrong spot. Sorry, -1/4, -2. And when I plug in 1, 1 to the third power, 1 and then 2 over that gives me 2. Then 2 to the third power is 8. 2 over 8 gives me 1/4. What do you think is going to happen if I were to plug in 3? Huh? It's going to be a smaller number. Is it going to be small and negative or small and positive? Small and positive. And so it's going to keep getting closer and closer and closer to what number? 0. What's going to happen if I were to plug in 1/2 though? If I plug in 1/2, what's 1/2 to the third power? 1/8. If I change flip, that equals what? So 1/2, 16. The smaller the number gets, what's happening to the y's? They're getting very big. That's what this side looks like. The other side is going to do the exact same thing. The bigger that x gets, the smaller my y's get. And the smaller that x gets, the bigger y gets. Not my best. Hopefully you get what I'm trying to get at. That's what these look like. This function is not the same as the other function. The exponent was even. This one's odd. It's a difference. Domain, what is it? A little louder. -infinity to 0. Union. 0 to infinity. You could also write it as x does not equal 0. Either way works. What's the range? Is it all real numbers? I'm asking. Is it all real numbers? No, it's not. There's a y value that is not ever included. It's 0. That graph will always get very, 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 very close to 0, but it will never actually be 0. So there's actually, just like with the other one, there's not only a vertical asymptote, but a horizontal one as well. So it's like it restricts both the domain and the range. So the range, 2, is -infinity to 0, with 0 not being included, 0 to infinity. Both of these will have asymptotes. And you said what? No intercepts. My end behavior. What's my left end behavior? What number? 0. And my right end behavior? Very good. Already did the continuity. Am I increasing? When I read from left to right, it's going down and it's going down. So that means if it's going down, it is, and it's decreasing from negative infinity to 0, because then there's a break, and then it's continuing to decrease after the asymptote. So you can't say from negative infinity to infinity because the 0 is undefined. Okay? Undefined. So you have to break it up. The main thing from this lesson is, can you successfully make a table? Can you graph these points? Can you analyze the information from the graph? That's really what it is. And if you have a general idea of like, okay, if it is a positive exponent and it's even, do I know what it looks like? If you have an idea of what it looks like, then you should be able to graph it. Okay? Give me a handful of points and then we're good. All right? All right. Radical functions, okay? A radical function is a function that can be written in the form of, as you can see, a radical, where the index is an n and the exponent is a p. Okay? N and p are positive integers greater than 1. That is a 1. They're positive integers that are greater than a 1. A p. So n and p are positive integers. You're not going to be dealing with any negative square roots here, okay, or negative indexes or anything like that. Now, power functions with fractions as exponents are known as radical functions as well. So if you have a power function whose exponent is a fraction, that technically is a radical function. Okay. So power functions that have fractions as exponents are actual radical functions. And this is what they look like. If n is an even root, so like a square root, a fourth root, a sixth root, etc., it looks just like the square root function. But if it's odd, it looks like like that cubic function turned on its side. It goes all the way through. Okay? So when n is even, the domains are always going to be from what to what? 0 to positive infinity, and 0 will be defined because you can't take the square root of 0. You just get 0. But if n is odd, the domain is going to be what? Negative infinity to infinity are all real numbers. Okay? So it's still, we are analyzing, but you'll have an idea of what it should look like if the root is even or if the root is odd. And we're going to look at one of each type. Okay? So we're going to look at 5 times the square root of 2x to the third power. We're going to look at this. Now, is this an even root or an odd root? Ah, that's the power. The power is odd, but look at the root.
Oh.
It's even. This is technically a square root. Okay? It's an even root, which means it's going to shoot off kind of like a rocket from 0. Okay? I cannot take the square root of negative numbers. Okay? I cannot take the square root of negative numbers. But I can take the square root of 0. When I plug 0 in, 0 to the third power is 0. 0 times 2 is 0. The square root of 0 is 0. And 0 times 5 is 0. Okay? That's why it is defined at 0. Now, if I try to plug in 1, 1 cubed is 1. 1 times 2 is 2. Is 2 a perfect square? No. So I'm not going to use 1 because I told you, you're not going to be able to use calculators for this. So you might want to pick a number that is a perfect square. Let's try 2. What's 2 to the third power? 8. What's 8 times 2? Is 16 a perfect square? Yes. So if I use that and I plug it in, I get the square root of 16. What's the square root of 16? And what's 4 times 5? 20. So already I'm at 0, 0, and then I'm at 2, 20. This bad boy, it is going to shoot off, but it's going to shoot like all the way out. Okay? Mm-hmm.
Oh.
It doesn't have to be like super specific, especially since, these are pretty much my points that I'm working with. It's increasing very fast in a short amount of time. What's the domain? 0, parenthesis or bracket. What's the range? 0, bracket or parenthesis? Does it have any x or y intercepts? 0, 0. Now this one, am I going to have two end behaviors? I'm only going to have the right end behavior, which is the limit as x approaches infinity of f of x. Because it's increasing without bound on the right side, but it's stopped on the left side. And where is it going? As x approaches infinity, y is going to equal what? Positive infinity. Very good. Is it continuous? It is, but it's not from negative infinity to infinity like the other graphs are. It's from 0 to infinity. And 0 is included. Is it increasing? From, and 0 is included on this time because it's an endpoint. Now I will say this: if you put a parenthesis around the 0 for increasing, I'm not going to penalize you, but I will for the domain and range because that is included. Okay. Is it decreasing? There you go. All right. We're going to do the last one together as well. Okay. And it is a 1/2 cube root 3x. Now, this is a odd root, so it's going to look like the odd picture, which means, yes, you can take the cube root of negative numbers, okay? You can take the cube root of negative numbers. The only problem is that, unless you know your perfect cubes, you're not going to get too many points out of this, okay? I'm going to help you out on this one, though. Let's do a negative 1/3. If you're like, a negative 1/3, why negative 1/3? Because what's 3 times a negative 1/3? Positive or negative? It's negative. You can take the cube root of a negative number. The cube root of negative 1 is negative 1. And that's why I chose that 1/3, negative 1/3. So what's negative 1 times 1/2? You're right. So at negative 1/3, I'm at negative 1/2. And let's see, what's another one? The only one I can think of is a negative 9. What's negative 9 times 3? Negative 27. What's the cube root of negative 27? It is 3, but because it was a negative 27, it's going to be a negative 3. And what's negative 3 times 1/2? Negative 1.5. So at negative 9, which is all the way over here, I'm at a negative 1.5. 0 is going to equal what? 0. And I can repeat the same thing. 1/3 and 1/2 and 9 and 3/2. You see it? It's hard to graph on this board. It is. But on my notes, they're going to be beautiful. Yes. What's the domain? What about the range? It's what? Sure is. Because the bigger that my x gets, my y's, they are going to get bigger. It's going to take a long time for them to get really big, but they are still getting bigger. Do I have any intercepts? 0, 0. Do I have both end behaviors? So the limit as x approaches negative infinity what? Negative infinity. Because it's not going to level out. It is going to continue to increase and get bigger and bigger and bigger. The limit as x approaches positive infinity is positive infinity. Is it continuous? On what interval? No breaks, no stopping point. Is it increasing? On what interval? To what? To positive infinity. Don't let that 0 stop you. Is it decreasing anywhere? And that is how you graph and analyze power and radical functions. Okay? I'm not going to penalize you if you don't have the table, but if your graph doesn't look anything like what it should look like, okay, then that's where the issue is going to come in, okay? So look at the type of function you're given, okay? If it is an odd root and a is positive, it should look like this. What do you think it's going to look like if a was negative, though? What if this was a negative 1/2 instead? It'll be flipped and it will look like this instead, okay? So you can even give me a sketch on your homework. When I say the graph, you can give me a sketch of what it should look like as long as it, as long as it goes as low as it's supposed to go, if it's supposed to look like one of the quadratic ones, okay? It's really more about being able to know what the graph looks like and analyze it, not so much graphing it specifically, but you're more than welcome to pick points. Any questions?